Okay, how are you? Do you have anything for me to collect? Please consider to bring it next time. But,
I have something.
good. So you
If you want it.
I do.
Okay.
I want to read something.
I just put my name on the one and then just snaps.
Okay.
No, there's actually some pages.
Mostly
in there.
Let me cover what I was ready to then consider it done to a certain degree so that you can spend.
I didn't complete it yet, but I didn't bring it to you. Can I do it
Yeah,
tomorrow?
you can just
Time?
scan and slide it on the door or scan and email.
Okay. We
Good.
have a practical tomorrow?
What?
Practical class tomorrow?
Yes. Yes, we do.
I can give you tomorrow then.
Okay, actually, can I have mine back for a second? I guess I want the pages of the actual homework, just in case we don't put it back, because then I can't remember.
But is it possible to still turn in homework?
Everything is possible. We are like colleagues here.
Everything's possible.
So, since we are colleagues here, you may consider to close your notes and complete a little quiz. So it's probably for 5 minutes. Please try to complete it, and as you do, I will make some comments about what is there. So last time we did consider density matrix equation of motion, and we are going to consider the same class of systems, a small, like couple of levels which can represent either transitions in atomic or molecular system or nuclear spin. It should be like 4 by 4, not 2 by 2.
Oh, yeah, you're right.
So we are going to consider same class of the system in 3 different representations. One representation is do not listen. It is only if you do not know what to write.
Oh, I do not know what to write.
But it will not help. It will just give some comments and navigation what is there. So same systems can be considered from the point of view of wave function, expansion coefficients, or from point of view of density matrix, or from point of view of Heisenberg equation of motion when one writes equation of motion for observables and solves it. And one of the critical things that we achieved last time is equation of motion for density matrix, which I will need to continue today's lecture, and we should rely on our collective memory. So you are basically helping me to start today's meeting. So the density matrix is composed of products of wave function expansion coefficients, and if you have 2 expansion coefficients, then there are 4 possible products, taking into account that one of them is conjugated. So there are 4 elements, and if you want to set up an equation of motion for it in form of linear differential equation, then to propagate 4 variables, one needs a matrix of 4 by 4. right? So the these elements, although it is a matrix, we can write it down in the form of a vector, and then write down like here which of the elements contribute to its evolution, like how much of this one contributes to evolution of this one, how much of this one contributes to evolution of this one, and so forth. And I know that it is a challenging task. I hate any memorization, and if you feel a little challenged with it, you may try to answer questions after this big box, and they may navigate you through and help how to recall. I will slowly start to do the same thing on the board, but then I will collect your work so that it doesn't undermine your grades if you have completed it.
Row in here refers to density of. What does row refer to? Row refers to some kind of density or.
Oh, we are missing another question: a definition of density matrix element.
Definition of row, density matrix or.
Is a coefficient on convolution term.
Yeah, feel free to
Level system, but what density properties of density matrix and its equation of motion. Okay. Is it always some kind of oscillators?
Oh, anyway, how are you?
Good, how about you?
Very good, very good. You are missing it here. Here is a way to entertain you.
Is it? Okay.
Okay. So if you feel that, if there are challenges, you forget something about the metrics, you can try to answer the question, which will navigate and help to complete it. with the quiz.
Pretty much.
Okay, so if there are no objections, I'm going to collect whatever we have.
No objection.
Thank you.
What?
Thank you for having no objection.
Oh yeah.
I will use one of these works as a cheat sheet for today's meeting, and whatever information you'll get will be based on your success or failure. 1, 2, 3. 1, 2, 3.
I could be totally wrong. I don't.
Well, not totally. Partially.
Is row 1 1 plus row 2 2 equals row 2 3 plus row 1 1?
I have no idea.
That's like what?
Well-
Addition doesn't matter, right? The question wants row 1 1 plus row 2 2. No, not row. P. Okay. P 1 1
Okay, okay.
plus P 2 equals question mark.
And then
Plus P 1 1.
Well, let me see.
That's true, right?
No, it would
It's hard to
be.
read in my matrix.
No. Well,
I don't. I find
I-
the definition of them. So
if you will be like gradient distribution, then you are safe. So there is no absolutely correct answers, but I cannot like punish for this because I'm not able to memorize long things. It's better to start from basic principle and then derive. So before we go forward, we need to feel these methods. So let's go through the questions and quickly answer them, and then we'll start new material after the end. So, what is? Someone didn't answer, or no? Okay. Jared did answer. Question number 2, correct.
Thank you.
So row 1 1 plus row 2 2. What is it? Huh?
Row 2
C 1 star C 1 plus C 2 star C 2 equals what? 1. Right? Yeah. Normalization. So there is 100% probability that it is either occupying state 1 or state 2. Together. Or if we are interpreting as a density, then, and we are talking about one particle, then it can be distributed, but it is only one particle. Then if we take derivative, d dt of 1 equals what? 0. Now we are fine with question 3. Okay. Therefore, row 1 1 minus row 2, just in case if we need it. But this is not part of equations. It is trivial. If we add together, then normalization can be used. So circle correct statements, and then most of them are silly, and there is only one correct. Okay, we are doing good on this. Not everyone, but some. Not everyone. Not everyone. So, compare row 1 2 and row 2 1. C 1 star C2 and C2 star C1. How do they compare? Yeah, so if you put conjugate here, they will be right? And it also, this explains that if we take derivative, if you want to propagate the off-diagonal elements, and we predominantly know that coefficients will be imaginary, then we just flip the sign and get another half of coefficients. So I wouldn't get full credit on this quiz myself. This it is a lot of memorization. Delta E over each bar. And here. So this one depends on itself. So it is cell number 3. Delta E over each bar. And this element that we put number 4 in the will be also I delta E over each bar. But they need to have different signs. Right? So if we set this one plus, then this will be minus. In case our system is not irradiated by light, or it is an NMR experiment that there is no transversal field, then all remaining cells will be zeros. So in absence of perturbing electric field, it is the only part of the evolution, accumulation of phase. So there are two types of elements: diagonal when indexes are the same, and off-diagonal if indices are different. In case system is not perturbed by light or whatever, if there is no external perturbation, if it is left alone, then there is only phase accumulation in the off-diagonal elements, and the rest are zeros. Now, question number 7. Who drives whom? Like, how does non-zero, I wouldn't say population, but something non-zero from one element transfers to something non-zero in another element? What are the rules of this transfer? This is operated by the Rabi frequency, and we are going to put here and there several of those symbols, right? So are we going to place any of these symbols in the block that couples diagonal elements to each other? Is there a chance to immediately move the population from excited to non-excited? No. And I'm not going to give argumentation right now. We derive this equation. If you right now you can open your notes, and if you have them, you can follow and correct them. So nothing is there, right? So this block is completely empty. Correct? Please correct me if I'm wrong, but I'm about to believe that it is so. And then there will be this Rabi frequency will help to change values of off-diagonal elements. If you have something in the on-diagonal, if there is something in the off-diagonal, and change the off-diagonal into something is diagonal. So I will write down for memorization this way. So the capital omega symbol stays in those cells that connect diagonal to off-diagonal and otherwise. Let's try to fill it. So we already have at least plus 2 zeros. And we have 8 symbols that are either all filled with omega capital or partially filled with omega capital symbols. And there should be different signs. One should be plus, another should be minus. So let's guess what should we have in the next two. It is the same principles that population in the non-zero elements in diagonal will originate from off diagonal, and because of this property, we just flip the signs. Minus A, plus A. Then how do we get non-zero elements in the off-diagonal elements if we start with ground state? As soon as we start to irradiate the system, all elements gain some non-zero value. But first it goes from, if there were non-zero values in the diagonal, then something will appear in the off-diagonal. So it will be same combinations, but we need to put the signs in the right way. And I'm getting lower grade, but I'm going to use cheat sheet for the signs. Okay, now we are equipped to go forward with the rest of the meeting.
So why did you flip the indexes here versus what we did on Thursday?
Flip the indices or rearrange put the elements in a different order?
Yeah,
Because it's
The final result doesn't depend on the order.
correct.
And I was reading different texts and they use different notations, but the logic in the order we used before is take the matrix and go row by row, right? 1, 1, 1, 2, 2, 1, 1, 1, 2, 2. And here the logic is to look on the diagonal first and off diagonal second. Then we have zeros condensed, and it is maybe easier to memorize, although it is not easy anyway. I don't know, unless you are practicing biological sciences and you know how to memorize large chunks of information. So what is the summary of our memorization? So how many zeros? 6. How many accumulation of phase? 2, right? Only here and there. And how many transitions stimulated by laser? Let's count. 1, 2, 3, 4, 5, 6, 7, 8. So total should be 16. Yes. 4 by 4 matrix. Okay? It is correct, but it is a little boring, exhausting, and as one of you told, mind name. Like you're getting a large amount of symbols, even if you understand what they mean. But what was the goal? Why did we start this activity, and why we continued in the meeting number 19 in CHEM767? What is the goal of quantum theory?
Predict observables?
Yes, yes. So which observables are we looking at for this class of systems? There's not much that we can design. Like which observables would be our goal if we would talk about, if you consider this mathematical model as a model for spin two-level system?
Population?
One. Huh?
NMR?
Yeah, for NMR, but which observables? Observables in a technical sense, not like prediction of chemical structure based on NMR, but very, very technical, limited observables. What we can get if we, what determines ability of this sample to respond to magnetic field?
Magnetization.
Yes, magnetization. Is it scalar or vector?
Overall averaged.
No, but
vector.
generally,
Well,
vector.
in
Vector.
general, it's vector.
We are living in space with how many dimensions? 3. So this magnetization has how many projections? 3. So we need observables equivalent to 3 projections of magnetization, which will be proportional to this 3 spin components of this one system. So we need S X, S Y, S Z. S X, S Y, S Z, and we need the expectation values. So the expectation, again, right now I'm going an adverse path of telling the story. There is a much straighter and logical, but everyone who listens to this straightforward and logical narration forgets it next hour because it seems so simple. If you go through a little longer, you will feel negative feelings towards what we do, but then you will memorize it. So it is not for presenting in public or in your presentations or in the thesis. It is like less pleasant, but helping for use it in the future. So the expectation values can be expressed in terms of wave function expansion coefficients or in terms of density matrix elements. We are going to write down both expressions for each of those. And if any of you know it by heart from the memory, you can write down the answer, or if you do not remember it, I can take like half a minute and rederive them based on the definition, which I repeat every time because I do not count on memory. So C1, 1, 0, 0, H1, 2, C, 2, C1 star, C2 star, H1, 2, 0, 1 star, C1, C2, So this one will be C1 star, C1 minus C2 star, C2 divided by 2, right? This one will be at the end of today's meeting, or maybe in the between, we will get such shorthand notation that can be memorized like 1, 2, 3. So there is not too many new ideas, but it will be very hard to go forward without this painful exercise. So, so these combinations of the expansion coefficients of wave function are practically needed to predict observables, right? And now we do have our definition of density matrix. And we can replace each of these pairs of expansion coefficient combinations two elements of density matrix, right?
How did you get on Z the over forward?
No, it shouldn't be here. Thank you. So this was in the wave function, and here we will write it down. As elements of density matrix. So here will be H over 2, 1, 2, 1, 2, plus rho 2 plus. This one will be H bar over 2 minus rho 1, 2. Plus I rho 2 1. And this will be rho 1 minus rho 2. So here's a little idea that maybe not very general today when we have powerful computers, but 60, 70 years ago, when one was trying to develop a theory for NMR and pulsed NMR, it was considered really fruitful. And it was time when one didn't have Microsoft Word to type in and copy-paste equations, when one needed everything in a very shorthand form. So, if we need only these three observables, why don't we write down equation of motion only for these observables, for these expectation values? It is an idea of Heisenberg equation of motion. But we are going from the back door instead of doing making commutator with Hamiltonian, we will use available equation of motion for each of those elements, and we will just combine them. So what we are going to do is to replace, plug in values from equation of motion for the density matrix into definition of observables. So here we can write the time derivative of this x will be time derivative of row 12 plus row 21. Time derivative of Sy will be minus row 12 is dot plus row 21 is dot, and time derivative of Sz will be row 11 is dot minus row 2 is dot. Right?
What did you,
No. I remember about you and possible question.
no, I didn't notice that you pulled out your eyes, so that's what I was.
So we are going to make one more painful step of looking to the far left and plugging it to the far right, using explicit expression for time derivative of each element of density matrix. Then we will plug in. And then after plugging in, we will discover a little surprise. We will see that the expression that we get can be formulated in terms of the same definitions. So one would form a closed set of equations for this x, y, and z components. Yes?
What happened to the 2 on the bottom and the SZ? Is that-
It should be here.
Go back in. So it should be 2 in total.
All of them, each, all of the two.
So for row 12, how do we write it down? We do have combination of diagonal elements with opposite sign and this factor of omega radian. Bracket. And here row 1 plus row 2. Right? And then there is one more term that corresponds to accumulation of phases. Now we need to do the same for row 21. So if you look on the equation that we have written down with our collective efforts, there will be again 3 terms. So will be two terms corresponding to diagonal elements and one element corresponding to accumulation phase. If you look onto the signs of the elements that make connection to population, they seem to cancel. So we are going to look on other elements right now, but immediately we can identify that here we have a subtraction of diagonal elements, right? And we know that when off-diagonal elements come with different signs, by playing with coefficients, one can bring it into S sub y element, S sub y observable.
Shouldn't it just be, instead of h bar, I down to e over 2?
Yes. But we are going to make one more step. Right now, we are writing down equation of motion for dimension-full observables, for spin components that have dimension of angular momentum, h bar. But if we define let's put any index this way. We can, and we may take derivative of it. It doesn't affect the constant. So one can remove constant from the left and right and keep the same equations. So we are going to get rid of this h bar, and the delta t or h bar is frequency. It's clear dimensions. But technically, yes, one can cancel h bar. So what are we going to get here for time derivative of the y projection? So we know that it will be composed of the same elements, row 1, 2, and row 2, 1, but with different coefficients up front. Minus I times row of plus I times row 1. Here, I can either think or, without thinking, just rewrite what is on the top. So what do we observe? In previous line, we were successful in finding this subtraction of the populations with the opposite coefficients. Here we have a little less luck, and this difference in populations come up with the same coefficients. So we can cancel them, but we can combine them and keep it here. Times I minus 1 is another minus, it will be plus, so it will be omega sub r divided by 2 plus the same term. So we can just remove 2 from the denominator and right here 11 minus 22. Now we do have these terms. How do we put some? We can write OH bar delta E, and here we have row 1, 2 minus row 2, 1. Let's check this. No. Here it was the same. Here were the brackets. And we have the minus I factor at the front. So I times I minus 1, another minus will be positive sign. So you have positive sign for the first term, the V or H bar, and for the second term, we have the real. It is real, and the sign is positive. So it is plus row 1, 2 plus row 2, 1. We are going to play a little bit more with factors and signs, but we can identify with a little playing. This one will be converted into S sub x. Here, this one will be converted into S sub y. And this one will be converted into S sub z. Right? So we are approaching our goal to have the closed equations only for these 3 observables. And if we derive these equations, we can forget the whole quantum theory. You can just, here is experiment, here is equation for observables, we solve and check if the outcome agrees with experiment. So for the last one, for S sub z, B we need time derivative of row 11, and we need time derivative of row 12, row 22. So let's pull them out of the equation of motion that we derived. So this one should be short. It will contain only Rabi frequency and mixing between diagonal and off diagonal. So it will be I omega per O2. One two minus rho 2 1. I have a suspicion that there could be something is missed here. Whew. All is good. By definition, there should be minus here, and then we have rho 1 2 plus rho 2 1. I just had a fear that we will get 0 here. I know by memory that it is not 0. So by combining these signs, we will see that these two combinations will add together. 2, 3, 2, omega r 2 factor I, and then we have rho 2 minus rho 1 factor 2 disappears. So this one will convert into which observable? Which of 3? When we have minus between off diagonal elements. This one? Why? This will convert into this.
Negative.
Negative?
It's on the first line.
Well, it is not yet a subway. We need to play with factors and make sure that we work with this imaginary unit and divide by 2 or multiply by h bar. We should carefully process it probably on the different board. But some of us need to go elsewhere in a couple of minutes, and I'm not sure that we will come to the next logical point by this time. So, I have planned for about a couple of steps more. So first we'll clean it up and write down the equation for this expectation values. And then we need to analyze the conservation of pseudo-spin. When we were talking last time, we did introduce so-called Bloch sphere, we were drawing solutions for this as x, as y, and as z as trajectories on a globe, on a sphere, right? Remember it? And the observation was that whatever we do, whatever regime of energies and intensities and pulse profiles, we always have trajectory with a fixed distance from origin to the surface of this sphere. So we agreed, or at least we didn't see deviation from the change of the length of this vector. So sx squared plus sy squared plus sz squared was always constant, right? After we complete the stuff, we are going to discuss is it always so, or there are some violations from this rule? Like, can pseudo spin become less than 1/2? This is a provocative statement. It has some trapping. So I'm going to clean the left board and rewrite this equation with all coefficients taken care of. I'm not happy with the first equation. Okay, no, I'm happy. So if you want to bring it to the form of S sub y, we need to divide and multiply by 2i, right? So we do want to have this shape. And we are going to remove h over bar, h bar over 2 because of this factor multiplication. So we will redefine lowercase sigma, same as s sub x, but without this h bar over 2.
But then we don't have sy.
Well, it will be all four, all three. H bar over 2 sigma y, sy, h bar over 2 sigma z, And then we can forget about this factor h bar over 2.
But then we don't have sy, because we multiplied by 2I and divided by 2I, so we can get to sy. But if we remove the h on top, then we don't have h over 2.
No, we will have it. We will have it. Well, we will identify we'll use these definitions. If you remove the factor, then this lowercase sigma will be just combination of density matrices without factors. So we systematically remove factor h bar over 2 from left and right part because it is just a factor. So this can be replaced to sigma y, and we are working with expectation values. I times I will be -1. -2. Total E over h bar. So we do see, okay, we'll analyze later. Now let's go to the second equation. No, we don't have water right now. It's inversion. Delta E over h bar. Right? It is what is on the right board. So here we do need to identify row 1, 2 plus row 2, 1 divided by 2, and we need to bring in factor 2 in here to have a correspondence. Then for y projection, and this one, if you divide it by 2 and multiply by 2, then we can identify this one as sigma z. Right? Inversion of the occupation of the levels. And then the third equation for the is subtraction of the off-diagonal elements, and we may want to divide by 2i and multiply by 2i to identify the sigma sub y. So it will be minus this. Let's go to minus. And if we would not make this redefinition, then we would get three equations for regular projections S, X, and S, Y, and Z. Yes.
Okay.
Thank you.
Okay, so who derived this equation? What's the name of the person who derived them for the first time? It is not written here.
Where did your H bars go? For your delta E over H bar.
Yes. Here should be. Frequency. Better? Okay, so what do we have here? And who did derive it? So it is optical Bloch equation or NMR Bloch equation depending on where you apply it. And if you are talking about spin, it is exactly what it tells, projections of spin, angular momentum. If one uses it for optical system, then it is pseudo spin, so it is same math but different objects. And the Sx and Sy would correspond to expectation values of transition dipole moment. So instantaneous value of the transition dipole moment. So let's discuss. We are not going to have more boring derivations today, but we will have a little discussion. So what if, how do these equations change in case the omega r equals 0? Then dsx dt equals sy, the dsy dt is plus delta E over h bar sx, and d z is 0. So if we are drawing solutions for any initial condition as the trajectory in three-dimensional space, then they will be on the sphere, and it will have the circular rotations around z-axis, no change in z projection, and it will be circles. So it will be keeping the same altitude but going around the globe, right? If we do have degenerate case, or if we are in the rotating frame and it is an exact resonance, then we do not have accumulation of phase, and we do have time derivative of the x projection equals 0, and the z and y components talk to each other and pass non-zero values between each other. So it will be sine and cosine solutions. So it will be circular motion in the sy sz plane, and sx will be kept constant. And if you have intermediate value, so those are family of trajectories for different initial conditions, that will come out of the Bloch equation solution at the condition of delta E equals 0. And if both constants are non-zero, then there will be pole where there is no motion will be in between SZ and SX, and there will be circular motion in this pattern. And when one is much bigger than another, then you have the very slow spiral that you were drawing in the previous meeting. Okay. I promise there will be no derivation, but there will be a little. Very, very quick one. What if we compose Sx squared plus Sy squared plus Z squared? And take time derivative. So if we plug in the derivatives of these components, what are we going to get? You can guess the answer, especially at the end. What are we going to get at the end? What are we going to prove in 30 seconds?
0.
Yes. We are just going to check that it is so. So 2 x times plus 2sy.
Yeah, you make
C. So there are two minuses. One minus is here, another minus should be here. Now there is a product x and y, and here is x and y, right? They are coming with the same coefficients up front but different signs. So this term and this term are cancelled. And here there is a y and z. Y and z. They have same absolute value of coefficient, different sign. Was here minus 3. So this will also cancel. It will be 0. Which means that we can set up a vector of S and its absolute value will be constant. So there are additional terms to the Bloch equation that would correspond to continuous shortening of the length of this Bloch vector. It means that if it is what Diane was asking a week ago on the lab, like if one strikes system with NMR system with big magnetic field, then stops any perturbation and measures how the magnetization changes with time. After some time, it will come to zero, to nothing. And there are phenomenological terms that correspond to this relaxation effects. So for the next meeting, maybe more than one, we are going to look on the origin, where these terms are coming from and how to understand it. Because if you take it literally, then this would mean that spin can be less than 1/2, which is a nonsense. So it is not spin, it is magnetization. And it is these terms in the equation reflect the fact that there is an average over an ensemble. So there are I don't want to erase this nice equation. So if you do have one driving electromagnetic field, or whatever, magnetic field of the given frequency, and this same field affects several systems, and they may have a little bit different delta E prime, delta E2 prime. And then, when we develop observable, we make a summation. So we do a summation over all members of the ensemble, and this summation is applied to each observable. Like S, X is index. We'll give the S X with two symbols of average. One average is quantum, and another is statistical average, because of the summation of the several representatives in the ensemble. So if we do the same, if you write this bar on the top, if you perform an average over ensemble, then it will be averaged spin projection and it will be average frequency, which will average frequency and average Rabi frequency, because transition of diagonal elements and energies are a little bit different in each representative of an ensemble. So our goal is to go from pure quantum description of an isolated system to an ensemble of multiple systems, and see how it will result on the observables, on the expectation values of observables that are really observed. Enough. It was too long. So meeting number 19 is complete, right?
Yeah.
So I'm going to switch it off in a second, but you're free to ask any questions. Let's see each other more at 6 p.m. in the lab, if you schedule allows.